So here we go again. The homework time. Ruler, pencil, pen, calculator, most importantly, because Miss keeps nagging about it, highlighter. Make sure I read the questions properly. Oh, we don't want my kidney still. So, kidneys. When kidneys fail, patients can live a relatively normal life as the functions of the kidney are performed by dialysis, which is the main form of treatment. And I remember doing that activity comparing hemodialysis, peritoneal dialysis and transplants, and then having to make that decision about who got the kidneys. Okay, I know where we are now. Hemodialysis. Connection is made to a blood vessel through which blood passes out of the body into the machine. So here we've got the blood going into the machine, blood coming out of the machine and going back into the body. Once in the machine, the blood passes through a system of tubes formed by an artificial membrane. Oh, there it is, artificial membrane, it's labelled for me, very good. So the blood's going through the artificial membrane, bathed in dialysis solution, which is continually replaced, okay? So my arrows are going in, out, in, out. So what's it telling me? So the blood is going in and going through, and the dialysis solution is coming in and going through in the same direction. Okay. Name. Oh, here we go, AO1. Name one substance that would be removed from the blood during dialysis. So in dialysis, what we're trying to do, and the method by which it crosses the artificial membrane. Now it's an artificial membrane, so it doesn't have any proteins in, phospholipids and stuff. It'll be something else, won't it? So I can't talk about active transport or facilitated diffusion. We're looking for something that's removed from the blood. So I know that one of the key things I want to remove is urea. That's the point. So it can only go by diffusion or osmosis. So urea doesn't move by osmosis, it moves by diffusion. Now we could also have perhaps salts on diffusion or water on osmosis, but urea is your main one, isn't it? So explain, give a reason why blood cells not be removed from the blood. Okay, so what do I know about blood cells? Well, they're quite big. They don't go through the normal sieving thing in ultrafiltration. So blood cells are too large to fit through the pores. The artificial membrane. Very good. So, what are we going to do now? Here we go. The dialysis session lasts for 4 hours, during which blood is continually being transferred. Oh, that was on the diagram, wasn't it? Arrows in and arrows out. From the body into the machine and return to the body. Okay, when we've got about 10 pints of blood, and so I'm thinking it's going to go through a few times. At the same time, fresh dialysis solution. So this is stuff that hasn't got urea in it. It's passed through the machine continuously. Okay, we've got two continuously things. Dialysis solution is composed of glucose with some salts. Might ask about that later, I suppose, glucose and salts. Typically, hemodialysis sessions are required 3 times a week. Using the information above and your own knowledge, dodgy ground there, explain, give reasons why hemodialysis is efficient. So, I'm thinking that efficiency of transfer, if I was talking about fission gas exchange and stuff, I'd be wanting to talk about countercurrent flow, but actually these two arrows are going in the same direction, so we're looking at parallel flow, but then we've always got some fresh solution going in, and we've always got some blood going through. So here we go. Blood is moving continually. Through the machine, past the dialysis solution. And then we've got fresh dialysis solution. Flows continuously past the blood. So really, we're going to be talking about concentration gradients. It's nothing to do with temperature, as it'll all be at 37 degrees. So this means there is a I don't want to write continuous again. I'm going to write there's a concentration gradient, and I'm going to write it in full because there's no such abbreviation as conc. There's a concentration gradient maintained and wastes. I'm just going to put urea. Can be removed all the time. Into the dialysis solution. So does that make sense? Let me just do a little doodle on my diagram. So I've got urea coming in, it's moving out into there, but then that's being taken away. So as the new blood comes in, even if it's got less urea, you've got fresh solution with no urea in it, so it will keep moving, keep moving. That seems fine to me then. Always going back just to check. So, an alternative method is peritoneal. I remember this one. This is one that takes place inside. Instead of blood being cleaned, and it's in inverted commas, and that means they don't really want me to use that term. Using an artificial membrane, instead of the blood being cleaned using an artificial membrane that's cleaned inside the body, is the peritoneum, thin membrane surrounding the organs of the abdomen, well supplied with blood vessels. But I seem to remember that when we did fish, sort of saying good blood supply, it was a bit rubbish, so I might want to say something else about that. Membrane has two layers, space in between used for the reservoir, so that's that bit there. But peritoneum, that's the membrane, organs. Principle, the fluid remains in the body for a few hours, after which you drain it out and replace it. So this is different. We've not got anything flowing through. You're tipping it into your abdomen and then waiting for a few hours and then draining it out and then doing it 4 times a day. Wow. So maybe for less time, but for doing it all the time during the day. So, explain. Explain why. Why is the peritoneum a suitable membrane for dialysis? So features of membranes that you want stuff to go across. Just tell me it was thin. So it's a thin membrane as a short diffusion path. Get that one down while I can. And then it's well supplied with blood vessels. So I'm presuming that because the capillaries are the site of exchange, it'll be well supplied with capillaries, and they'll be running next to the membrane and close capillaries, so urea can diffuse easily into the dialysis fluid. And of course that will be other things as well, like salt and water, but the idea is it's not got far to go. Okay, I think that will do. Using the information provided and your own knowledge, or not again. So I'm going to be using this information and what I know. Suggest why peritoneal takes place 4 times and hemodialysis 3 times a week. So why do we need to do this more often? So what did I say the big difference was? The big difference is it stays in the body and then it's drained out. So what do I know? That the urea will come out of the blood and into the dialysate until they were equal concentrations. So we're not taking it away, we're not taking the dialysis. So when it fills up with urea, it's not going to remove anymore, and it's just putting that into proper words then. So the concentration gradient, let's start with that. Concentration gradient is not maintained. As the dialysis fluid remains, what did it say, in the body. Equilibrium can be reached meaning no further wastes can be removed after a few hours. So it has to be done more frequently. So it has to be done more frequently. That kind of covers all bases. Oh, on to the last little bits. Suggest one of those questions. How the dialysis fluid may be altered to allow more water. So if you want more water, we're always going for water from high water potential to low water potential. If we want more water, we're going to have to make that lower. How can we do that? So it's just a suggest, isn't it? So let's say add more solute so that water potential, and I am going to write it out in full. I know I could use that little psi symbol, is lowered, and you could also use more negative there if that's what you're more comfortable using. Water potential is lowered. I've deliberately not said what solute because I just can't think of one. And all I'm thinking now is urea and glucose, but I don't want to put urea or glucose in because they'll then just start diffusing into the bloodstream, and this would be a bad thing. So I'm just going to add more solute and hope that that's enough. So, moving on, if peritoneal dialysis is used for long-term treatment, peritoneum becomes thickened. Suggest how and why. And then we're going to use this word efficiency of dialysis. So how will it affect it? Thickening will make the dialysis less efficient, because thickened, I'm thinking, the diffusion path will be longer. Now with all these go through videos, can I just suggest that you actually go back through the question, you highlight the things that I've highlighted, and more importantly that you make some corrections, preferably in a different coloured pen. Good luck.